Our next topic here in geology is called fossil fuels, and fossil fuels are where we get all the current most popular forms of energy that we use today, things like petroleum, natural gas, coal, etc. And since we're on the topic, I'd like to talk about some alternative energy sources that are available as well. So let's begin with looking at what fossil fuels are, and then talking about the different fossil fuels. Fossil fuels include oil, coal, and natural gas. They're formed from the remains of once living organisms. They supply about 80% of the U.S. energy requirements, and demand was spurred by the Industrial Revolution. Oil shale, tar sand, and methane hydrate are other fossil fuels that may provide a huge resource of energy down the road. Pictured here are a couple of pie graphs that show the United States energy consumption by source, noting that petroleum is the greatest amount of energy producer, or the greatest amount of energy is produced by petroleum, excuse me. And the electricity, transportation, industry, residential, and commercial, these are all the ways in which energy is used in the U.S. Let's get into the specifics of petroleum and natural gas. Petroleum, or crude oil, provides about 36% of the U.S. energy supply. It's not a single composition, but usually has a range of hydrocarbons and that are in long, complex chains that can be filtered out and used for different purposes, such as not only gas and oil, but plastics as well. Natural gas is made of a short hydrocarbon chains, and it is often found with petroleum deposits. Natural gas includes methane, ethane, and propane, and this provides about 27% of the U.S. energy source. You can see a little schematic of the geology of natural gas resources there, and how we see natural gas resources from specific layers under the ground that produce them. So what is necessary to produce an economic deposit of petroleum or natural gas? Well, marine organisms are necessary. Petroleum and natural gas ultimately come from marine organisms that die and have their remains fall to the seafloor. The organic remains must be buried quickly by sediment and decay under oxygen poor or reducing conditions. And under increasing pressure and temperature, organic molecules break down or crack into simpler ones. And so that's what's shown in the schematic and the diagram here. You can take a couple of minutes to look through it. You actually, in addition to the fact that organisms produce oil and petroleum and natural gas deposits, you also need a rock layer that can hold that oil and natural gas and actually allow it to be pumped out of it. And so that's called a reservoir rock. You need a high porosity reservoir rock that has a good permeability, ability for us to draw that material out in order to store oil and gas. And it has to have a low permeability area above it to kind of trap the oil and natural gas underground, to keep them so that we can grab them before they come to the surface. So what you see pictured here is a reservoir rock with the oil and natural gas in it, and then a cap rock, quote unquote, that doesn't allow water or liquids to flow through very easily, and that acts as a cap to hold the deposit in. And so the oil and gas migrate upward through the reservoir rock and get trapped by the cap rock. There are a variety of ways in which you can form a trap for oil and natural gas. The picture here shows several ways. You can have a fold, pictured in the upper left there. You can have a fault, pictured in the upper right. You can have a lithologic or stratigraphic oil trap, where different rock layers form an unconformity with the rock layers below, providing a trap. And then you can also have salt domes. Salt domes often occur when you have large rock salt deposits underground. They are actually less dense and more buoyant than the rest of the rock, and so they have a tendency to push upward as the rock layers are formed, and eventually forms kind of a dome shape. different areas that have this situation often have rock layers that form traps. When pure petroleum is extracted, it's put into a refining tower or a cracking tower, and when this happens, they heat up the petroleum and it vaporizes, and the different vapor produces different material. As it vaporizes, the heavier stuff sinks to the bottom and the lighter stuff floats to the top. The stuff we use for gasoline is kind of the least dense material. That's at the top of the cracking tower, and at the bottom of the cracking tower you get heavy oil and asphalt, stuff that they make roads with and things like that, and all the different materials in between. The U.S. has about 50 to 70 billion barrels of proven reserves. 1 barrel equals about 42 gallons. The world has approximately 1.1 to 3 trillion barrels of oil of proven reserves. The U.S. has probably less than 5% of the world's total. You can see that Saudi Arabia and Venezuela are sitting on oil gold mines there, and there are some other areas around the world that have significant reserves as well. The U.S. consumes about 7 billion barrels of oil per year and about 20 trillion cubic feet of natural gas. The world rates are about 30 billion barrels of oil per year and 80 trillion cubic feet of gas. The U.S. consumes then about 25% of the world's petroleum and natural gas, which requires us to import both. The United States, you can see in the lower left, is the greatest user of oil and consumer of oil, and then the top 10 annual net oil importers, the U.S. is at the top of the list. Estimated total resources are 2 to 3 times the proven reservoirs. We think these will begin to run out about 2050 or so. And you can see pictured here when different oil reserves will run out for particular areas of the world. About 20 to 40% of the initial oil reservoir gets pumped out, and this is what we call primary recovery. So all those proven resources, we pump out about 20 to 40% of that, and that's kind of what we consider kind of the primary recovery. Now, you can actually increase the amount or percentage of oil obtained from a reservoir by using some secondary recovery procedures. One common one is for water to be pumped into the reservoir to push the residual oil towards a production well. But there are other methods such as hydrofracturing, opening fractures with high pressure water, explosive fracturing to shattering the rock with explosives to help get more of the oil out, gas pressurization, which forces oil towards the well by injecting high pressure gas, hydrothermal techniques using hot water or steam to heat and thin the oil, making it easier to flow towards the well and pump, and chemical additives. All these secondary recovery methods can be used to significantly increase the recovery amounts from different areas. So the proven resources we talked about on the last slide can be nearly doubled by the secondary recovery procedures. Let's discuss coal. Coal reserves meet about 20% of U.S. energy needs. Prior to petroleum and natural gas, coal was pretty much the dominant energy source. It fell into disfavor during the 20th century. Proven reserves are about 70 billion tons, estimated 10 trillion tons, and the U.S. reserves are about 200 billion tons, estimated about 2 trillion tons. In fact, the U.S. has the world's single biggest supply of coal, and we have consumed less than 5% of our reserves, so we still have hundreds of years of supplies of coal to produce energy. Coal is formed from land plants, whereas petroleum and natural gas were formed from ocean organisms. Coal is formed from swampy or tropical environments that initially have peat that gets buried at the surface, and under reducing conditions, the buried material over time with pressure and temperature and time increases the grade of coal from peat to lignite or brown coal, then to bituminous coal or soft coal. As the pressure and temperature and time increase, you end up at anthracite or hard coal. Each grade of coal increases the energy content within the coal. If you cook the coal too much, though, if you get too much temperature in there, then you get pure carbon in the form of graphite, which has no energy value at all. So it's kind of an interesting little balance there. One of the reasons that coal fell into disfavor in the 20th century was because of some of the problems associated with it, particularly environmental problems in mining. Coal typically contains high sulfur contents. It results in acid mine drainage. Burning coal leaves a residue that contains about 5 to 20% toxic materials in the residue. Of course, mining destroys habitats when we look at strip mining. And underground mining is, of course, hazardous to miners' health, and we've seen many examples of that. And combustion of coal produces an increase in the amount of carbon dioxide in the atmosphere, which is, of course, something we're trying to reduce. Techniques are being developed to burn coal cleaner, and when we run out of oil, it's likely that these techniques will be perfected because where the money is, so goes the business and the energy production. But right now you can see here in this picture that coal goes in, it's gasified and burned. Some of the material is removed and the pollutants are removed and used for different industrial uses. The carbon dioxide is also absorbed and used for other sources as well and other uses. So you can see that companies that are working on trying to make coal lucrative, they're really trying to find ways in which to burn coal cleaner, which is, of course, a good thing. Now, aside from coal and oil, there are three specific non-traditional fossil fuels that I want to talk about. We have oil, petroleum, natural gas, and coal that we currently use now, but there are others as well. Oil shale was not kind of referred to in some of the proven reserves of oil, but oil shale refers to kerogen, which is a waxy hydrocarbon in shale, and we have a lot of that stuff around. Much of it actually is in the U.S., estimated at 2 to 5 trillion barrels. Tar sands are another fossil fuel that can be obtained, and this is much of this is in Canada, in the Athabasca tar sands near Calgary. But it contains a semi-solid tar deposit that can actually be used as an energy source. And then gas hydrates, crystalline solids of methane and water ice found in deep marine sediments in Arctic seas, are plentiful. And of course, many are located in international waters, so there'd be some issues with that, but there are definitely some other fossil fuels out there that can be used. So fossil fuels can be used for quite some time in our world. There are also many alternative energy sources that are worth a look, and so let's take a look at some of these that are present and things that we can gain from them. Because the fossil fuel resources are limited and an increased demand for energy, as well as the efforts to try to reduce environmental impacts with energy sources, there are some other options. Nuclear power through the form of nuclear fission and nuclear fusion, solar power, wind power, hydropower, and other biomass and geothermal and hydrogen fuel cell sources can provide energy. Let's first talk about nuclear and solar power. Nuclear power really is actually probably the best potential alternative energy resource. Essentially, there's two types, nuclear fission and nuclear fusion. The kind of reactors we have now are nuclear fission reactors. It basically takes uranium-235, and that nuclei divides when in contact with a neutron uranium-238 spontaneously splits apart. And when it does this, it releases some energy, and that energy produces heat, and that heat then can be used to turn a turbine or heat up water to form steam, which can turn a turbine to form energy. And so that's basically how it all works. Nuclear power plants, we've heard in the news, do produce nuclear waste, and so that's an issue, finding some place to dispose of that. Although it can be stored pretty safely in designated locations, there is kind of a taboo about that, but it actually, when you look at the environmental impact and cost of human life, it's very much less than in most all other energy sources. Additionally, we've seen some nuclear accidents, and there's been 3. You can count on one hand the nuclear accidents out of all the nuclear power plants in the world, and all of those were because of gross human error. So those are things people have learned from since then. So believe it or not, nuclear power is one of the most promising types of nuclear power, or of energy source. Even more promising than nuclear fission is nuclear fusion. In nuclear fusion, deuterium or tritium fuse together to make helium-4 nucleus, and when this happens, a little bit of that matter is converted to energy, and even a little matter creates a ton of energy. And so nuclear fusion is a really good way to produce a lot of energy quickly. It only requires just a little bit of matter to produce a lot of energy. That energy, of course, then heats water, which forms steam, which turns a turbine to produce electricity. Really, we have a virtually unlimited resource of hydrogen from water for the fuel, and fusion products are not highly radioactive, so there's it's pretty clean as far as nuclear power goes. They're still working on it, though. This is not something that's been perfected. It's very hard to produce nuclear fusion, because it requires a lot of energy to get the atoms to fuse. So they're working on, you can see a picture of an example of a nuclear fusion plant there. You can see how there are basically an electromagnetic field that controls the fusion reaction within, creates heat, which creates steam, which turns the turbines. Solar energy is a clean, unlimited source of energy. It's little or no pollution of any kind is produced. The basic idea is we have a photovoltaic cell. It's a solar cell that converts sunlight into electricity. Currently, photovoltaic cells are inefficient and expensive, but they're getting better. Essentially, the solar radiation hits one part of the cell, creating an electron flow from one part to the other, and this produces energy. Again, very clean, but still pretty expensive at this point. Let's take a look at wind and water. You've seen many of a wind farm here, especially in DeKalb County. The wind turbines, when pointed in the right direction, produce motion from the wind, and that turns a turbine, which produces electricity. Wind, of course, produces no air pollution and is renewable. It is one of the fastest growing sources of energy globally, still only really accounts for a small portion of our energy production. It is more expensive than using fossil fuels, and wind is unpredictable and dispersed, so you need large arrays of wind turbines to produce enough energy to be helpful. And the energy must be stored. When the wind is calm, you have to have had enough energy produced to meet the energy needs. Solar really has the same issue. You have to have a sunny day or a lot of sun to produce a lot of solar energy. Hydroelectric power is another source of energy that is pretty clean and useful. Essentially, you build a dam across a river, build up a high amount of water on one side, and let that water go through a small area to produce movement of a turbine, which creates electricity. This is a very good sort of model. Fast flowing streams are preferred over the dam model, but nonetheless, if you turn a turbine, you're going to produce energy. Tidal power, wave energy, and oceanic heat also produce motion that can be utilized to turn turbines to produce energy, but these are only useful in select locations wherever you have coastlines. Let's take a look at biomass and geothermal energy. So biomass energy is really just burning wood. Original source of energy for humans. It's still used extensively all over the world. Of course, it does pollute the air and remove trees from the landscape. Agriculturally produced fossil fuels like alcohol from grains and methane from animal waste take away from food production and often can be more expensive to produce. You can burn garbage instead of putting in landfills, but of course that produces a lot of carbon dioxide when you burn it. Essentially, all biomass is renewable, but it has a major drawback, and that is burning them produces carbon dioxide, which is a greenhouse gas, and our goal is to reduce the emissions. So biomass isn't so promising in that regard. Geothermal energy is pretty efficient. You concentrate and extract heat from the Earth's upper crust in regions where you have magma near the surface, and it's usually associated then with hot spots or plate boundaries, and it's economically competitive and largely pollution free, but of course it's isolated and limited, and when an area cools or erupts, the power is gone. But nonetheless, it's pretty useful, and just like any of these other sources, it's useful in specific areas around the world. So if you're able to do it, do it. Let's take a look at hydrogen. Hydrogen fuel cells are another source of clean energy. Water can be broken down into oxygen and hydrogen by electrolysis, and also can combine hydrogen and oxygen to produce electricity and water. Hydrogen fuel cells can be used as a battery to make fuel, and you can make fuel cells for home use, for your car, for personal electronic devices. You need hydrogen distribution systems similar to what we have for gasoline, but and this is a promising sort of alternative, but really there won't be any wide use of hydrogen fuel cells until there's a demand for it. So there are options available if and when we run out of fossil fuels in the near future. So that's a look at fossil fuels, particularly petroleum and natural gas and coal, but noting that there are other fossil fuels that are usable as well. There are also alternative energy sources such as nuclear, which is very promising. Solar and wind and water can also turn turbines or produce electrical flow for energy. And biomass and geothermal we talked about a little bit, and then hydrogen fuel cells. Very interesting stuff when we talk about energy, but thankfully there's lots of sources of energy available and ways that we as humans can produce energy to suit our needs for the future and beyond. So thank you very much for listening, and we'll talk with you soon.